Good morning, ladies and gentlemen, although there are only gentlemen here. Today we will be talking about math, the past, the present, and its limitations, by me and Kushagra. In this presentation, we will be covering the introduction, the past related to math, its historical breakthroughs, the present, the current breakthroughs which we are currently working on, which the world is working on, and what might happen, the future, what we could expect in the future of math, such as like four-dimensional graphs or something. Current limitations, what is limiting us to not do this right now, like not create breakthroughs and whatnot. What are the limitations of math? What are the points of math which don't just work? And lastly, description. Can you describe everything using math? This is the topic of today's debate, which should be explored later on in the presentation. Introduction. Math. Today, mathematics is a problem-solving tool. This allowed us to solve some of the hardest challenges of the time. This ranged from setting a place value system all the way up to complex numbers. Hell, even the concept of infinity. Here's the past of math. In 2000 BCE, the place value system was invented. The place value system is a type of system which allows you to represent the value of a number based on its position. So, for example, the further a number is to the left, the more valuable it is.
Right. So it's like we still learn that, and it was like 2000 BC. So it was like around 4000 years ago.
Place value system was the thing which revolutionized numbers and mathematics at the start, and this is the system which allowed everything else to be invented.
Right. But see, I mean, it's fascinating how we are still learning it, and we are like still, our math is still based off it, and this was invented like 4000 years ago.
I mean, of course, it would be. I mean, it is the foundation for all of mathematics. Like, if you don't have this, you don't have anything. Not
Yeah.
even addition. Like, now you can't even do 2 plus 3.
Uh-huh.
Euclidean
Interesting.
geometry was invented in 300 BCE. Euclidean geometry refers to whatever we learn in mensuration in geometry, stuff like areas of triangles, circles, the perimeters, the ways you can construct them. Yeah,
Right. So
algebra.
basically, okay.
Well, all of y'all know about algebra. You're learning it already. Calculus. Calculus being originated in the 1600s by Sir Isaac Newton. Calculus refers to is the study of instantaneous rates of change in behaviors of functions. This
So,
allows you to This allows you to closely examine what happens near the domain of a function and how sensitive a function is to sensitive changes.
right, so it's basically a
1650.
study of graphs kind of thing. Because functions are
I
plotted
wouldn't
on graphs, and it's a study of functions.
I
So,
wouldn't say so, but sure, I guess that's one way to put it.
right.
So, concept of infinity. Well, infinity is like really big. So, for for a while, the largest number people could think of was like 100 or 1,000. When the concept of infinity came around, it revolutionized everything. It allowed you to get to infinitesimally close points. It allowed you to approximate the values of certain constants really well by taking limits to infinity and what stuff like that. In the 1650s, at around the same time as this, imaginary numbers came up. How? By a certain Cardano. Cardano was a scientist who found the solution for the qubit, not the depressed qubit. That's Antion. That was the teacher of Antion del Ferro. So Cardano was the one who came up with the full qubit, not the depressed one. For anyone who's wondering, the depressed cubic is the same cubic equation without the x squared term. For example,
Right.
x squared plus 3x plus 5. That's a depressed cubic. Whereas
That's
a full
very
cubic,
depressing.
well, yeah, sure, it is. So whereas a full cubic is like x cubed plus 3x squared plus minus 5x plus 12 equals 0. The full cubic. in the 1800s, non-Euclidean geometry was invented, and this is the type of geometry which is completely different from what was discovered in 300 BCE. 1 second, I need to sneeze. Okay, one sneezing session later.
So
I thought I needed to.
what's the difference between non-Euclidean geometry and Euclidean geometry? I mean, geometry is like a study of material
Yes,
things, you could say, right?
I'm getting to that. I'm getting to that.
Shapes,
Huh?
So non-Euclidean.
shapes, shapes,
Shapes are.
shapes.
Yes,
Shapes.
Why
shapes.
would they study you?
Ha ha
Because
ha.
both of them are related to shapes only though. Non-Euclidean geometry, however, all of the Euclidean geometry is written on a flat plane, like circles, squares, rectangles, and whatnot. Whereas for non-Euclidean geometry, imagine drawing a triangle on a sphere, like, and then which like actually like is on the, what do you call it, the surface area of it, and then try measuring the angles of it.
Right. So basically, geometry
It's
on
really
non-flat
on
planes.
certain, yeah, kind of like look. No. You're not getting my point. You're not getting my point. I'll annotate and show you. So if you have a sphere, it's kind of like this. Imagine this is a sphere, okay? So you know how this would like bulge out a bit?
Yeah, makes sense.
Yeah, so these angles will be like add up more than 180.
Right. So the plane is like not uh
Level.
planar.
2D, two-dimensional, two-dimensional, two-dimensional.
Right.
And lastly, in the 1900s, set theory and mathematical logic was invented. Now, set theory refers to like the axioms or the rules of the mathematical system. Stuff like the set of all for this is like chapter 8 in my textbook, and it's the worst chapter in history. So this allows you to like give relationships like A union B and stuff like that, and
Right.
it's absolutely horrendous. So yeah.
Hmm.
Oh wait, wrong.
Nah. While mathematicians invented imaginary numbers,
You failed to impress your imaginary girlfriend. Did you know mathematicians used to represent stuff like x cubed? Like imagine taking like, so in the olden days, yes, I will call it that. So to represent cubic equations, they didn't use stuff like x cubed and 3y squared and stuff like that. They used the literal cube with side length 3.
that is fascinating.
And then, so algebra back then had a more geometric representation.
Right. The equations could be represented using like figures.
Yeah, it could. So, like for example, take the equation x squared plus 7x plus 12. So take a square side length x, and then
Right.
take a line which is 7, and then cut it in half, 3.5, 3.5. You add it to the whole thing.
That
Like I'll
resonated
annotate this.
in my brain.
Most people would learn this in like 8th grade or something. I'll show you.
Bro,
So
after seeing this Tesseract, I'm telling you my brain is not braining.
of course
What
it's not.
brain rate?
You have brain x. This is side length x. You add a side length of 3.5 because well it's 7x, right? So you cut it in half. So you can get two halves like this where you can add like x here and 3 here, 3.5 at least. And then you need to add a bit of square to complete it
Right.
because it's a square. And this square is 12.
The square would be 7x, right? Because
No. This whole area, not this side length, the big length here, which you cut in half and you put it on the either side of this square like this and this. Excuse me for my horrendous drawing. I can't draw on a laptop. So like this whole area is 7x.
right.
So if you cut it in half, this part is 7 by the way. So this length will be 3.5 and this
Uh-huh.
length will also be 3.5. So you get x times 3.5, x plus 3.5 on both sides. So this whole thing would be x plus 3.5 whole square minus this thing which is not there.
Right.
So
And that thing should
yeah,
technically equal to like 7x.
yeah, kind of like that. So that's essentially what completing the square is. That's an example of how math used to be in the olden days.
That's like a plus b whole square, but on a square. Like
Yeah, like
on,
literal square.
that is fascinating.
I wonder how they represented higher powers, such as 3 to the 4. Well, it's this. Well, that's the neat part they did it.
I don't think they use that to represent higher powers. Sorry, Atis,
I don't
again.
I don't think higher powers existed at the time. Me trying to find the longest side of the blanket at 3 goes as the present of math. Present. In today's technical world, math has tons of applications. From stuff like finance all the way up to physics. Now, obviously, I expect you to read the slide because I'm not going to read all of this out. With these many applications of math in all industries, it's no wonder no one wants to get a job. The problem of unsolvability. So there are questions in mathematics which are completely unsolvable, kind of like the Collatz conjecture. The Collatz conjecture is a conjecture which is really cool in my opinion. You should totally check it out once. It essentially says, so you take any number, and if it's odd, you apply this process. You do 3x plus 1, and the
Where
number you
x is
get,
the number.
yeah, x is the number which you input. If the number which you get is even, you divide it by 2. If it's odd, you conduct the 3x plus 1.
Right.
So like if you start with like 16, for example, but because 16 is odd, you divide by 2. You know, I
You get
shouldn't take a power of. I'll take a different example. Let's say you take 12.
sure.
12 by 2 is 6.
Yes.
6 is
And
also even.
yes, so we'll
Uh,
get 3.
3. Because 3 is odd, 3 times 3 is 9. 9
9.
plus 1 is 10. 10 is
Right.
even, so you divide by 2. 5. 5 5 is odd, so you multiply by 3 and add 1, you get 16. 16 by 2 is 8. 8 by 2 is 4. 4 by 2 is 2. 2 by 2 is 1. 1 is odd, so you multiply by 3 and add 1, you get 4. And then you
Wait.
see, you just
From
so you
4
just
you got 1, and then from 1 you got 4.
yeah, exactly. So it's a loop. Now
Right.
the Collatz conjecture, it says that the Collatz conjecture asks if there is a set of numbers which leads to itself, other than the 4 to 1 loop. Like all numbers, it's kind of like a never expanding tree.
Right.
Imagine this is a tree. Imagine this is a tree. This is a tree, and now we have what do you call it? Now we have like a separate like circle of these numbers. This one leads to this one leads to this one leads to this one leads to this, and so on. Doesn't
Uh,
matter how big the loop is, it just has to lead to itself.
Right.
Yeah. So the thing is, there are unsolvable questions like this in mathematics, and mathematics are kind of scared of them.
Okay, so there are some problems that cannot be solved.
They cannot be solved. Well, at least haven't been solved yet, at least.
Right.
This is a quote. Words full of wisdom, someone important said and can get the reader get inspired. We couldn't find or make a math code, so this is all you have to get inspired.
Okay, your voice seems to be going like really low.
Oh, sorry. Can you hear me now?
Yes.
Now,
Can you repeat? Can you repeat what you said earlier?
the problem of incompleteness. Mathematician Kurt Gödel proved that it's impossible to prove certain things. I don't understand what he meant by true statements, but I'm sure it's something. With second incompleteness theorem, he proved that you cannot verify system's credibility. So, like something like, so you see the complex numbers, right? It's sorry, I'm taking a wrong example. You should think of like math as a whole. It's a system.
Math
Yes.
is a system, yes.
Now you cannot prove that math is a formal system, in fact, not a regular system. It's got axioms and rules and all. So the thing is, you cannot verify that whatever this system is doing is correct with with the system's own resources. So what we're saying is that we cannot prove 1 plus 1 is true just by using statements like resources.
What do you mean? Also, your voice is breaking again.
Excuse me for my horrible internet. Could you hear me now?
Yes.
Now, so basically, it's impossible to prove certain things, even though you know that they are true and you know that they've existed for millions of years. You just can't prove it.
That's interesting.
This broke the heart. Yeah, this broke the heart of many mathematicians, and Godel never got any more mathematician day chocolates ever again. I meant to do Valentine's Day, but then mathematicians day. Get it?
Right.
Get it? Yes. Description of math or reality. Can everything be described using math? Well, this is the topic of debate. I hope you guys have some pretty interesting, I don't know, points
Okay,
to discuss.
what are your points?
The,
Can math describe everything? What are your thoughts on this?
I don't think you can describe everything using math, because think about it. When you say everything, first, I think for the purposes of this discussion, we should define what everything is, because everything is kind of vague in this sense.
Right. So
So, what do you
how
suggest we define everything as first?
the natural world, the universe, the fundamental laws of physics, and possibly quantum mechanics, you could say.
You mean all intangible and tangible processes happening in the universe?
Yes.
Okay. So I'm just gonna quickly do this. That's how do I make this bigger? Okay. This is just for reference.
Right.
Um, yeah. Could you see this properly, or is it like a bit unclear? Or should I move this actually? I don't know how to move this.
Now you should move it.
Yeah. No, you can't move it. Whatever. It's fine. So all tangible and intangible things in the universe. And what should I define things as?
What do you mean by things?
Exactly, that's the point. What should I define things?
I think
Action.
things could mean phenomenon, uh,
Sure.
objects.
Okay. This I don't want to write this again. So whoever. So well, fine, whatever. Yeah, that should make everything clear. Now,
Right.
the point is that math cannot be described. Math cannot describe everything, because can you answer me this question? Answer this question for me. Can you describe a biological system completely, like the nervous system, the respiratory system, using a set of
Using a set of?
equations and stuff,
I
like
believe so.
functions? So okay, fine, you might have one for heartbeat. Okay, so like
What I
so
believe
for
is that there might be too many constants involved, like there might be too many factors, but after an extinct, you can define all of it.
but the problem is, here's the thing. Okay, if you want to describe everything in math, you there are systems too complex to do so. So in order for you to do that, you must make some assumptions, and what is the word I'm looking for? compromise on some of the accuracy.
I don't think you have to
Because
compromise
if
on the accuracy.
you need to take some assumptions at least. Like if you have a sufficiently complex system, you will have to take a couple of assumptions such that your system works out, your mathematical equations works out under that assumption. Whereas the assumption, if the assumption is proved false, then all of your equations is for nothing.
Right, but when you take the body example, right, there are some facts about the human bodies, right? Those facts can be
Yeah,
used
there
as
are
assumptions. And if the facts are like correct, like if the biology is correct, then I think we'll get proper equations.
yeah, but in a system as complex as the human body, there are tons of things which are there are tons of things which are just variable.
Right. But I think all change
For
can be
example,
calculated.
here's the thing. Another example I'll give. Okay, fine. I'll take the human body example again. You think you can make an equation for everything in the human body,
Yes.
given sufficient assumptions?
Yes.
Okay, then how would you give an equation for emotion?
Emotion.
Yeah,
By
emotion.
emotion, you are referring to the amount of release of different liquids, I guess you could say.
No, but can you establish a relationship such as like given the circumstance?
I think so. There must be some proportion or ratio between the amount of
But
happiness a
the
person
thing is,
feels
you're not
and
getting my
the
point.
situation
Okay,
a person is. Huh?
it's not exactly what I'm trying to go for. Sorry, I said it wrong. So the thing is, emotions are mostly random. Well, at least depending on the situation, right?
I don't think so, no.
I
I
mean,
mean,
depending
if
upon
I
the
get you a
situation.
present, let's say, then there are high chances that you'll feel happy about it, right?
Yes, I will be happy about it. But how could you describe happiness in a variable?
By the amount of dopamine released, I guess.
But the thing is, dopamine doesn't only control happiness; it controls other things as well.
Well, uh, I bet there is some molecule that controls happiness.
It is dopamine, except dopamine controls other things as well. So how do you differentiate dopamine with other things? Dopamine controlling other things.
Well, I mean, if dopamine is released, then those other emotions you speak about should also be released, right? So to an extent, they'll also be released then.
I don't actually know about that. Okay, I'm gonna research about that.
Exactly.
Yeah. Hmm. Well, I guess we can go to the next slide.
My views, mine only, not yours. Okay, now I'll give my views, mine only.
This is a point for me.
That's what, see, math describes physics, right? Physics can literally translate to Greek. Like, physics is literally in Greek, study of the real world, right?
Yeah, I see your point, but like, but physics is like saying all how do I say this? All vegetables are plants, but not all plants are vegetables. It's kind of like that.
True, but see, math can describe physics, right?
Yeah,
What else do
math.
you expect math to do? Why was math invented? To describe the real world.
It is to
And
quantify things.
yeah, and it is doing
To
that through
quantify
physics. And
physics.
see, here's one more example. You know how we have like video games, right? And
Yeah.
recently they have tried incorporating AI into video games. So the characters think that they are
Yeah.
real, right?
Oh no, it's been going on for ages.
No, but before we had NPCs,
I see
now
it.
now we have AI.
Oh my god, my finger. So I
So
put my finger in a shelf and I closed it on my finger.
that is an ingenious thing to do.
Yes, yes. Okay.
So
Yeah.
anyways, back
Sorry,
to my
going
point.
off.
So game developers have like started using AI in games to make the characters feel that they're real.
Yeah, but how is
Now,
this relating to math though?
just hear me out. Now, what
Yeah.
if we are living in such a game? It is possible, right? And the game runs completely on 0 and 1 binary numbers, right? Now, binary number is just another system. It's another mathematical system with another base. We use the base 10, right? I mean, when you go to 11, like when the second digit comes in or the third digit comes in, it's on the basis of 10. In the binary system, it's on the basis of 2. So if systems like those use binary systems, then they are using math, and it could be us. So we can kind of say that our universe could be
Are you
completely
wait
based off math.
I'm gonna have to like quickly just intercept you for a moment. So isn't it base two when I'm gonna assume what you're saying is true for now, okay?
Sure.
Here to affected magical people controlling us using binary systems.
Yes.
Then how do you expect
Not controlling us, but
but like a simulation of sorts.
what I mean is that the universe could have a binary code behind it. Like everything that happens not because of the code, but everything that happens is registered in the code. Like like a star
You
explodes,
no,
right?
you're not getting my point.
Okay, continue.
What I'm saying is base 10. Okay, first let's get things out of the way first. Base 10 is more efficient than base 2. Do you agree with me?
Yeah, so the universe could be using some other base as well. I don't think that's exactly related because base 2 could be seen as an example.
Yeah, base 2 could be seen as an example, but like what you're saying, sure. I mean, this is kind of philosophical, but we've gone slightly out of topic, but like still, uh, it doesn't math. It's just numbers. It's just base 10. There is logic. The best thing to make logic out of is base 2.
Right.
Yeah, it's the best thing to make logic out of.
Why?
I mean, because there's only two possible states, so
Right,
there's
that makes
less states
sense.
to focus on. But the problem is, it will take more memory storing large amounts, higher numbers.
So what we're talking about here is the universe to us. I
Yeah,
think
exactly.
to
But the
create
but the
a
claim but the claim of the but the claim that the universe is made out of binary numbers is simply preposterous, in my opinion. I mean, people can say that you're not opening your mind or something, but still, have you seen proof for it?
have you seen what?
Proof?
Well, no, but if you look at the multiverse theory, every time you choose one of the two given options, a new universe opens up. So that means that there is a
I don't know the
possibility,
multiverse theory. I don't know about the multiverse theory that well. Could you please give me a small briefing?
right? So it basically says that every time you have options and you choose something, a few number of universes open up, like new universes just get formed, and everything is the same except that you chose the other option.
Oh, kind of like an alternate timeline kind of thing.
Yes.
Okay. I've seen that kind of movie before. I think the movie will help in explaining it though. I
Uh,
don't know right now.
I don't think I've seen the movie. Anyways,
Yeah.
what I'm trying to imply over here is that the universe might run on code, and every time we have like options,
Are
we
you
might
saying that
get
the Are you saying that the universe will run out of RAM?
not exactly.
Because that is woefully off topic.
I don't think the universe can run out of RAM. I mean, if you have a thing this big and conservation of matter follows, the amount of RAM always stays constant, right? Because there's like a specific number of options you have.
So you're considering energy to be the RAM.
Not exactly, but I'm considering RAM to be proportional to the amount of energy and matter specifically.
Well, there's only like 13% of like real like tangible matter. The rest all is like dark matter and stuff. No.
Well, matter is matter.
Well, we have less than a minute, so we better like
Sum it
end
up.
it.
Yeah.
So thank you guys for listening today. We hope you enjoyed our debate. This is the Dora the Rock. WWE is very logical though. Well, see you guys.